useful information. I'm really happy that you decided to spend your Saturday morning here on this webinar, workshop, whatever it is. I'm Alex Honchar. I'm a machine learning practitioner. I'm working in this field for some time. And basically, today I would like to share some experiences, some ideas in machine learning in finance. And basically, for the organization of this event is more responsible another guy, Marco Scaravelli. He is one of the organizers of Machine Learning Milan meetup. Basically, this is the non-profit organization. The guys are really making good events, and in Milano, and they want to be like really make it a good community of practitioners, entrepreneurs, scientists in Italy, and they also a group of Italian Association for Machine Learning. Basically, I was a speaker myself on these events. I am happy to help with some sort of co-organizing and making good content. So if you guys are interested, you can follow the page on the meetup.com, and should be interesting. Basically, with the latest news of the viruses, etc., we don't know if it is panic or maybe there are some conspiracy theories about it. We don't know. But actually, this event is supposed to be offline first, and it should be like a long for 6, maybe 8 hours. Basically, we are thinking about making like whole Saturday thing. But with this news, we decided to make like first part online. So guys who are maybe kind of doubting about the topic, they can check out if it's difficult, not difficult, and maybe get some idea about the topic. And later, hopefully, you can organize it offline. So basically, today, finance topic, which is online, as you can see. And in 2 weeks, there will be another meetup, online meetup about generative adversarial networks. Actually, this is what I'm going to watch myself because this is the second topic. Which is also very interesting for me. And so basically, this is about the meetup organization in general. The link to subscribe, follow, etc. is in the description. A couple of words about me. As I said, I'm working in machine learning field, and I can describe myself as first I was a practitioner because I started as the engineer, as the research scientist. I was publishing some papers. I was working as the developer on some projects, and basically today I can say I know how to do something with the data, and I'm more or less confident that I can deliver the results, which is a good point. Also, lately I'm trying myself as the entrepreneur. I'm building the distributed consulting company, which is something different than just normal outstaff or outsourcing. We can talk about it later. And also one of my passion, which is I'm doing regularly and for free, is like blogging, doing workshops like this, giving some lectures in universities. This is what I really like. Basically, I'm a big fan of the area of machine learning or artificial intelligence, and I'm trying to give some impact and get something back, of course, basically as the developer, as the entrepreneur, and also as an educator in the field. And my first question to you guys today actually I'll ask a lot of questions, so I really would like to build it as some sort of communication thing. I know we have just a chat, but I'll read it, I'll answer all the questions, and basically this meetup will be really flexible in terms of the results. So to make it the best for you, I also want to know a bit about who are you? Are you working in finance? Are you working in machine learning? What do you expect to get today? Because basically, I can change the material more or less on the fly. So if we see that most of the people are interested in something else, what they prepared, we can easily fix it. So if you guys can say something like about you, what are you working on, your experience, ideas, what you expect from today, it would be really nice and useful. Yes, you can see the organizing is here in the chat as well. Hello, Marco. There should be some delay in the stream, so most probably I'll answer like in, I don't know, 10, 20, 30 seconds, but it shouldn't interrupt our process. I'm checking the chat now from my phone. Okay, I'll just write up as a list, so at the end we kind of can check if we achieved what we wanted to do. Okay, no experience. About software engineer with no experience in finance at all. Okay. Okay, maybe one or two more, and I think I already more or less understand the profile. So basically, I hope I got it right. Basically, yes, I'm expecting to come people who have at least some experience in machine learning, to be honest, because today there will be some mathematics, basically some applications, and I didn't plan to talk about how some neural network or logistic regression is being trained. Basically, I wanted to talk more about the applications. So I expect you guys already have the idea, okay, we have data, we can put it in the model, we can fit the model, we can predict, check the accuracy or some other metrics, etc., etc. So hopefully that's okay. Finance consultant. Okay, good. Crypto assets. Experience response. Yeah, combining the both worlds will be actually not that straightforward, as you will see. I'll just wait, 30 seconds more due to delay, and we'll move forward. Yeah, that's good. Basically, with this kind of experience, I really expect that you guys will be able to. For example, if you're not planning to work in finance, I really think that you at least today catch up some ideas about general machine learning. So basically, because in finance, there are some tricky moments that are actually can be useful in the computer vision, NLP, whatever you do as well. And if you plan to do something in financial world, not necessarily actually in trading or like bots or something like this, I hope it will save you some time and it will allow you not to make some mistakes that, for example, I did when I was just starting. Okay. No finance. Basic quant and okay, that looks good. I think 90% what I prepared already fits. Something else we'll try to do on the fly. So basically, what this workshop is definitely not about. As I said, we are not going to talk about machine learning algorithms at all. Basically, I expect that you already have general idea or maybe some advanced idea that you can have historical data. For example, you can have pictures of some objects and the labels. For example, this is the picture, this is what this object is, and you can build some algorithm in between that can input the picture or the text or the time series or some table, whatever it is, and output something which you want to predict from this. So I expect you've seen the examples on the internet of face recognition, voice recognition, Tesla, deepfakes, whatever it is. Also, I really don't want to dive into mathematics today. There will be some formulas, definitely, but I will give the reference to the books because we have just 2 hours. And even if we had the whole day, I really want to give theory really briefly. And you can dive into the theory more as a homework or if you feel interested in this. Also, we're not going to talk about anything like infrastructure, bots, and actual trading today. Basically, today, I want to really focus on a small part which is related to the modeling of financial data. Basically, the idea why I started kind of even to talk about this topic and to show because when we do machine learning on normal data, on pictures, on text, basically what we do mathematical modeling. we have some empirical data and we want to find such a mathematical model that can describe this data. For example, you can take the analogy from the physics. There are some motion of some physical body and there are differential equations that describe this motion. Or there is some body and there is the set of equations that describe the surface of this body or something like this. The same actually what you do guys in computer vision. There are some pictures with the faces, for example, and basically what does your favorite convolutional neural network? It learns the formula that describes some high-dimensional surface of the faces in order so later, based on this formula in form of neural networks, you can recognize the faces, for example. So basically today I want to concentrate on the modeling. And as you will see, there is no easy ways. I will not show you any recipe or something. I'll think that I'll show what I think and what some other practitioners, my colleagues think is the right way to approach the market data. So hopefully this will be good. And actually what it is about, will be about adapting everything what you guys are going to do with data from now and in your future tasks. Basically my main goal today is to show you how really deep you can dive into details and how really normal and adequate data machine learning pipelines that you use now that work for you, that you put into production, that work, and they did work with the normal data, they will fail horribly in financial machine learning. And to me, so to say, perfect outcome from today is that you guys, when you next time approach any task you will do, you will remember some points about how tricky can be the preparation of the data, how tricky can be choice of the labels, how tricky can be work with the algorithm, how tricky can be evaluation, how tricky can be evaluation of the, so to say, business results. So I don't know if you'll be really positive about results, but hopefully it will be at least interesting. So the plan for today is I want to briefly say about the jobs and tasks in finance, because I see that you guys, okay, maybe you didn't work in the hedge funds or at banks. So I want to show first that there are much more things apart of trading, apart of like buying cheaply, selling on the big price or something like this, because banks, hedge funds, financial institutions, they have to do a lot of things and machine learning is really useful there. So maybe you'll be also interested in other applications. Then there will be a lot of practice, and the focus of the practice will be showing, okay, this is classical ML, this is how it might work in finance, then I show you that it don't work and we fix some mistakes and learn some new things about machine learning and finance, understanding why it's different. And we'll iteratively practice, see the results, understand why they're wrong, check a bit the theory, fix the results again, and come up with something what is more and more adequate. And hopefully when or if we'll organize the next part of the meetup, which will be longer, I would like to show like the full pipeline, because today it will be the introduction. I'll show just some techniques and actually I'll give you the homework. But later I would like to show like the full solution, at least the framework. Then I also would like to talk a bit more about theory on the full event. Basically, you know, finance is driven by some mathematical models. I know it can be some simple time series models like ARIMA, it can be stochastic differential equations, it can be econometrical models. And basically, I would like to, I can spend like 1 hour talking why this is not very adequate, this years of science. And again, a lot of practice beyond predicting the price or something like this. This is the general plan. I hope this is okay, guys. If you have some questions or you want to comment something or you want to, I don't know, want to get something new or something else, please say in the chat and we'll also add it to the plan. As I said, I want to be really flexible, and if you have some specific questions, I want to answer them and potentially show you something as well. So let's spend, I know, 1-2 minutes on the questions if there are some. Yes, if no questions, if everything is clear, just say, let's go, and we'll just move forward. Thank you, Enrico. I hope it's really okay, the plan. Okay, seems like everything is clear. Let's move forward and go quickly through the general part so we can start also quicker the coding. Okay, basically this is the picture that is maybe looks a bit outdated now, but I think to me it really shows well what are the jobs in finance. This is like the table about mostly banking jobs. As you can see, there is front office and back office, and buy side and sell side. Basically, if you read the descriptions, you can see that the front office is the people who are basically doing the trading itself. They're or buying something, investing, they're creating some financial instruments, they're doing the active job. And the back office is obviously the support. As you can see here, is like the data scrapping, server administration, some technology, risk management, basically some these kind of things. For us, from the financial point of view, will be more interesting the difference between buy side and sell side. So what is buy side? Basically, this is the people who are focused on the, roughly speaking, again, this is not 100% correct term, focused on the investments. And they get large bonuses for the successful investments. And by investments, I mean that why it's called buy side, because they want to find such assets or some financial instruments that you can invest in. It doesn't matter long or short, and you can get some profits from it. And the sell side is another, because, for example, what is the buy side is doing? There's the people who want to invest in something. They want to invest in the stocks, they want to invest in the options and some other financial instruments, and gold, crypto, whatever it is. But these financial instruments, for example, indices of stocks, for example, it can be some portfolios, it can be options, some derivatives. There are some another financial institutions that are actually creating some financial instruments and they're selling them to another investors. And basically the banks, for example, then can issue some derivatives, they can issue some instruments, so another investors can buy them if they find them profitable in the future, or at least they can estimate the price is good. So today we're going to focus a bit more on the buy side. Basically, we're going to try to understand based on some time series if this particular instrument, if this particular stock is going to be profitable or no, so to say. But it's good to see the big picture as well. Applied directions, again, in general in the fintech, which includes also not just investment management, not just trading, but also banking. You can see also more big picture can be described here. For example, in the banking, a part of the financial operations themselves, there are some retail operations. For example, basically, if you go to the bank, if you're a client, they also sell you like the credit cards, they sell you the credits, they sell you the insurances. So basically, working with these products is also part of the job. There are peer-to-peer operations. For example, basically when you send money to someone, can be fraudulent operations. So detecting if some credit card payment is fraudulent or no, it's also important fintech task which can be solved with machine learning. And also lending money and credit scoring. Basically, if you want to borrow some money from the bank obviously want to score you and estimate the probability of you basically returning money or no. Second thing is asset management. Also, you can consider this as so-called classical investment. Basically, this is on the big picture is if you have some cash or some capital and you want to invest it, most probably you want to diversify it somehow. You want to say, okay, I want to invest part of my money in the gold, part of money in I want to buy a couple of apartments, I want to invest in the stocks, I want to invest in the crypto, I want to invest in my friend's business, and something like this. And all these options, you can consider this like the different markets with different options where you can put your capital and expect it to grow, obviously. And obviously today, there are so many potential options, so the data, if you want to do it in a quantitative way, the data is very high dimensional, different markets and different possibilities. So representation learning, to learn somehow the more comfortable representation of the market to see where you want to invest, it's obviously machine learning task. Portfolio optimization with respect to some goal. This is another really old and classical area. Basically, okay, you found some options. Basically, okay, I can invest in 100 different possibilities. And actually, you would like to invest into them all. But some of them are risky, some of them are less risky, and you want to kind of balance it. And this balancing with respect to some goal, and the goal can be I want to maximize my returns, whatever the risks are, or you want to balance between the risk and the profit, or maybe you want to diversify your portfolio. It's different optimization goal. And this is also maybe not machine learning, but it's optimization, industrial optimization. And of course, risk management, because okay, you have your portfolio from the crypto, gold, stocks, apartments, whatever it is, and you obviously know there are some risks, and you want to minimize them, or you want to deal with them somehow, you want to cover them maybe, or you want to eliminate them at all. This is task where can be used machine learning, can be used some mathematics. This is also important thing. And of course, what I think you guys must probably, when someone is thinking, okay, machine learning in finance, must probably think about the trading. You want to forecast the price. So if you know that it's gonna grow, you can buy now and say sell later. If you know it's gonna fall, you can short it. So basically, this is like a classical thing you might think about. Optimal execution is also a tricky point because, okay, maybe you can forecast that the price is gonna grow at some moment, but when exactly you want to buy, right now or in 1 hour, or when exactly you want to sell, this is also like a task you need to do optimally, so it's not that straightforward. And a part of the forecasting itself, you want to have the whole strategy around it. You want to understand the risks of the forecast, etc., etc. So this is also where machine learning can be useful. And since the trading is something what we're gonna touch today, this is usually what is not doing a single guy, like he's just downloading the data, running the models and creating the strategy, and then everything goes cool. Normally, from my experience and what other practitioners are saying, there are these groups of jobs as well. Analysts are the guys who are maybe even not programmers at all, they're just the guys who know finance, and they look at the markets and they select, for example, potentially growing industries, or they try to find the factors that are influencing the market. For example, if you talk about crypto, it can be the guy who is monitoring the chats in Telegram and he's saying, okay, I can see that the analysts in Telegram are actually really confident and their forecasts are good. Let's use this data to forecast the crypto. Or for example, in the current situation, analysts can be the guys who say, okay, look, all the markets are falling. The job of analysis is to find the assets that are growing. For example, the pharmacology companies, gold, again, crypto, and something like this. Then when he gets this idea, he's given the idea to the data curators, who basically their job is to download the data related to what analysts are saying. And then two jobs that we are going to talk about in depth today are feature analysts, is the guy who are taking the data, extracting the features, and are actually building some models already. Basically, they're modeling the data in order to predict something. And then the strategists are the guys who are taking the models and using them to build a strategy. Basically, they're saying, okay, if the model has the probability more than 0.6, then I want to do something. Again, and this is where the data scientists are doing their job. Then backtesters, they are not necessarily data scientists. They are also, I would say, financial experts that are taking the strategy and they basically try to show that the strategy is bad. They're running the strategies on some historical data. They're trying to simulate some possible scenarios. Basically, their job is to understand all the risks and all the possibilities of the strategy. If it's good at all, to give it to the next deployment team, which is just engineers who, for example, connect. They're making the data source. For example, if you want to trade in real time, they need to make the real-time connection to the data source, they connect to the exchange you're going to trade, etc., etc. And then when the strategy is deployed, in practice, you almost never have just a single strategy based on a single neural network. You have a lot of different strategies. And there is a guy who's called portfolio manager, and he is kind of overlooking all the strategies already in deployment with knowing all the risks, and he's balancing between them. So these are the trading roles. And applications of machine learning in finance are basically the following. They're classical. Supervised learning, we want to predict some numerical value to classify something. Supervised learning, maybe want to cluster some time series or cluster the market, or to learn the less noisy representation of the market. And reinforcement learning, of course, since we want to do some actions on the market, or we want to, for example, in trading, obviously we want to do some actions. So this is the territory of reinforcement learning. And here I just also to give some examples of the tasks. For example, regression is to predict the earnings of the company, the credit loss forecasting, price forecasting. For the clustering, you see customer segmentation. This is example from the banking. Basically, for example, for the credit scoring, you would like to cluster your customers into different groups, or stock segmentation. Stock segmentation can be also in different form. For example, you want to cluster stocks who kind of are similar. For example, you have a lot of options, and you can cluster like crypto assets together, some internet companies together, technology companies together, and textile companies together, and something like this. Also, there can be classification and representation learning. These are the typical tasks that you might see in fintech in general. And the data that you might see in the market, and not just in the market, is the banking data, is the fundamental data. By fundamental data, I mean that when you see the stock price of some company, okay, this is like the public price, this is the company is public, so the shares of the company are available to buy or sell in the open markets. But this is like just the visible part. This is what's supposed to explain how valuable or not valuable the company is. But behind these prices on the Yahoo Finance or something, there are the assets that this company owns, their liabilities, their amount of sales and earnings of the company. For example, let's talk about Apple. Apple, you can see that the stock price is down the last days. Okay, you can say coronavirus, you can say it's a panics, but actually there is a good economical explanation as well, because Apple has a lot of factories in China, and since in China there is some problems, people are not working there today, and the management of Apple is saying, guys, we are not going to earn that much this year because of obvious reasons. And since the Apple is not going to earn that much, why should I hold the stock of the company that's not going to be profitable? I want to sell it. So of course the price of Apple is drawn in. Again, market data, these prices, the amount of trades, the dividends, etc., etc. Also, there are interesting alternative data sources. For example, there are a lot of analytics online and from the experts, and you can use this, for example, so to say, to analyze the crowd wisdom, what other people are talking about some data, so maybe there is some sense there. And also there is alternative data. For example, you can analyze video imagery from satellites to understand, for example, the activity of the company. You can analyze Twitter, etc., etc., etc. Okay, this is the introduction about this is the general intro. If you have some questions about it, let's discuss it. Guys, any questions related to the general financial tasks and what machine learning potentially can do there? Or let's just go to the practical part. Guys, and also if there are some problems with the connection, please let me know, because when I'm showing the slides, I don't see the statistics, and seems like for 10 minutes I was offline or something like this. I don't know, so just let me know. Okay, just a couple of feedbacks more and we'll move to the coding. Okay, if it's all clear, I would like to show notebook. Hopefully it will be visible. Just want to check. In finance 3 years ago. Basically, this is the normal machine learning pipeline. And what we have here. Okay, here is the data related to the Apple stock. This is like the end. It's from 2000 to 2020, not including the latest problems. You can see there are some classical data from the market, high, low, open, close. Basically, what is high, low, open, close for a day? In a day, basically, obviously have like a lot of trades within a one day. And the price of the Apple or anything that you trade anywhere can change during the day. And the high, low, open, close, for example, open and close, it means with what price the market opened today and with what price the market closed today. And high and low corresponds for the highest and the lowest price on the market in this day. This is the daily data. Volume is the amount of sales, and also I've added some another features that might be useful. For example, here are some features like financial indicators. You don't have to worry about it. Basically, it's just some formulas applied to the prices, and also some alternative data like fundamental data, data from the financial reports, sentiment analysis, amount about the dividends, etc., etc. So we, so to say, have a bit more data about the market. And as in any machine learning task, I want to split data into train and test, which is obvious. And I have data from 2000 to 2020. So, okay, it's reasonable that I do take, for example, most of the data to train from 15 years. And then on the last 5 years, I want to test my algorithm if it can actually predict something. And you can see that the data will look like this. Basically, this is the raw data, not normalized, nothing. There are different features, etc., etc. Yeah, some data looks kind of random, but it's because it's based on the changes. So basically, but it's the data. Okay, normal data preparation pipeline. I want to scale my data. But obviously, I know from the market that, for example, the prices and I know that the situation on the market is usually changing, right? So statistics is changing. So I can't say that, for example, that the volatility in 2005, 2010 will be the same as in 2015 and 2020. The same I can say about the minimal, maximal data, etc. So that's why I can't fit my scalar on the whole data set together, because it will be overfitting to the statistics from the future. So that's why I fit my scalar on the data from the train on 15 years, and then I use the scalar on the data, obviously on the data from the past. Past, I mean historical data that we used to train. And I use the same scalar with the same statistics from the past to normalize the data from the test set. So this way, I don't make a look back in the future. This I do with the inputs, with the variables, and the same I do with the prices. Since I want to forecast the price, I want to normalize the prices in the same way. I use the close values, and again, I fit my scalar, new scalar, obviously, on the train data and use it on the test data. Another thing about finance also that I understand that from a single price or from a single variable in this day, maybe I can't forecast the future, because the price, this number of $100 tells me nothing about what will happen in the future. But if I take, for example, some historical window of some days, for example, 2 weeks, 1 week, maybe this way I can catch some patterns that will be helpful to forecasting. That's why I want to use the window of 14 days, which is 2 weeks. I want to use 2 weeks of the data to forecast the next day. That's why I use this hyperparameter of window and horizon, where window is the historical window and the horizon is the forecasting horizon. Just want to check the comments. Okay, everything's fine. Yeah, so here I'm just going in the loop, where I'm taking these windows. For example, I want to make a data set now. And in the data set, I want to go with a sliding windows through this time series, taking one window, for example, of 14 days as the input. And this window is not just, this window is of all these variables stuck together. So taking this window as the input, and as the output, I take a normalized price 1 day ahead. This is the thing that we are not going to use today. I was just playing with it. So basically, yeah, that's what I do. Then I save these windows. I save this forecasting objective. Basically, this is my X and Y, input and the output. That's what I want to train the model for. And this I'm just saving also the price in this moment because I'll use it for some sort of backtest. Then separately, again, I don't want to look in the future and I want to mix my data sets. I use input train and output train, input test and output test to create these data sets. And basically this is my Y. This is what I want to predict. This is the normalized prices. This is the prices I want to fit on, and this is the prices I want to test on. It looks more or less adequate because you see in the trained data, okay, yeah, the price is always growing, so we expect to work even better than this. But for example, in the training data, there are ups and downs, and in the test data, there are ups and downs. So we expect that it will work out somehow. This is really easy. Again, maybe a bit tricky part is here, but this is just sliding window. You can see I'm looping over the data set, over this time series, which is like every day I have a lot of variables, and I'm taking the 2 weeks of these variables as the input and one close price, normalized price, close price, because I want to forecast with what price the market will close 1 day ahead. That's I'm taking the E plus my horizon, which is like the next observation. So I created my data set, and since I like neural networks, I want to apply a very simple neural network, building Keras. The architecture, as you can see, is very, very simple. Since my input is a matrix, because I have 14 days of 16 variables, it's a matrix, I have to flatten it into a single vector. Okay, this is can be done with the flatten operation. Then there will be one hidden layer. Then I want to regularize my model, obviously, that's why I apply dropout. And my dense layer output one is basically the one forecasting. You see, I use here a linear activation, which means no activation, because my price in the future that I want to forecast, even if it is normalized, it's basically it doesn't really have the bounds. That's why I want to forecast it as a linear layer. Also, one important moment, obviously in the future, you can see the prices are scaled. That's why I saved the scaler for the prices as an object here, because later when I'll check my accuracy, obviously I'll check the performance not on the normalized data, but on the actual prices. That's why I'll restore the statistics. Okay, question, what the scaler does? Basically, the standard scaler, it takes, you see, for example, if you check the close price here, you can see it is in the range from 0 to 300. And machine learning works the most well with the data that is in some fixed range. For example, what is the example of the fixed range? All my data has values from 0 to 1. This is the fixed range. But if I squeeze my prices like to everything be from 0 to 1, I might lose some information. That's why another approach to normalize it, is to normalize it statistically. Basically, I want my data to have zero mean always and some fixed variance. That's why to every sample in my data set, I subtract the mean value and divide by standard variance. So this way I kind of standardize my data. So it always has zero mean because subtracted mean, and the variance will be stable because it's divided by the variance. And this is what the standard scaler does under the hood. So that's why, for example, when here I check my close prices, this is already normalized data. It always will have the... And for example, if in the future the price will go up or will go down, it will be already used this mean and standard deviation fit from this data set. So in the future, they also adapt the input data to what you already have here. Okay, let's train the model. It will be done relatively quickly. And while it's training, I'll show you what is the evaluation part. Okay, the model is trained on the past data, then I want to predict based on the test set. Then, as you can see, I want to restore the original price range. Because, for example, if I want to do or model some trading, I want to use not the normalized price, because this is like normal. I do normalizing just to make the machine learning easier. To do my, let's say, financial experiments, I will work with the normal prices. That's what I do here. I restore the normal prices. Then I check the accuracy. Basically, since I want to forecast the price, I want to see the error in the dollars, basically the mean absolute error, and the R2 score, which basically how much of the variance I explain. You can treat it as some sort of unbounded correlation. Basically, this is how much variance inside the data I explain. And obviously in scaled data, you can see that the error, the mean absolute error is 0.13, but it's not adequate because it's the scaled data. My actual error is $4, absolute error, obviously. And actually we can explain a lot of variation. Looks interesting. Let's check at the graph. The graph also looks like, okay, the blue is the actual price in the future out of sample, and the orange is my forecasts. And it looks like we actually can fit the data pretty well. So R2 score is not lying. The $4 on where the prices are like 300 looks adequate. So looks like, wow, cool results. If you try to do some primitive backtest of the strategy, it will not look that good. I'll just zoom it a bit. Blue line here is supposedly portfolio when we buy when the price, then we predict here that the price will go up, and then we sell when we predict the price will go down. Blue, this is our portfolio, which is actually falling, and yellow is what would happen if we just would invest in this apple and just keep it growing as it's growing. So what's the problem? Why we have such a perfect performance in terms of the metrics, in terms of the graph, visual explanation, but if you start trading, it will fail. And this is basically what I found out several years ago. Unfortunately, to my shame, I was publishing such results myself. And if you Google, for example, like machine learning stock market prediction, and for example, if you check, you see on YouTube, you can see kind of more or less the same thing. If you check the top blogs that appear in the Google, you will also see something what is similar. And I can tell you guys, I'll leave you as a homework. You should check the academical papers that are peer-reviewed articles, and they do the same. They show the same metrics and they show the same pictures. I just want to show you one of the examples to see that we kind of do the same what people in internet do. And they show, so to say, good results. So, what do you think, guys? What we did correct, what is wrong, etc., etc. I'll just answer the questions now, but also please let's think what is wrong here. Did I try different window lengths or 14 as standard value? Basically, I took this window length of 14 as out of my head. Of course, in practice, you optimize this value. In some markets, you need to check within a week. In some markets, you need to check within a couple of months. I just, out of my head, I think that maybe looking in the couple of weeks of the data, I can more or less estimate what will happen tomorrow. So this is just a guess. The price at 300 is well outside the training distribution. Isn't this a problem? Well, it could be a problem, but since we use this data, when we train the model, we normalize this data. So actually, we can say that we use the statistics from the data. So this 300 is normalized. So it shouldn't be. Even normalized data will be also high, so it means that the price is simply high. That's how data is. So what do you think, guys? This pipeline, what's the problem in this pipeline? Because we did everything what other bloggers do. You check the academical articles, they do in most of the cases the same. But when I try to run simple simulation of the strategy, it fails. And this is how my research on the topic started. What's the problem? And I will leave this picture open because this one is even a bit better. So you can try to think what is not correct here. Because the trick why not predicting plus 2-3 days in the future? Yes, we could predict 2-3 days in the future. Again, this is the option as well. But, I just want to show something what everyone does. So, of course, all these hyperparameters you need to do more carefully. I just want to show that we do normal machine learning pipeline. We normalize the data. We separate train and test. We do it carefully. We run the metrics. The metrics are cool, but in fact, this is shit. It will never work in the future, and I would like us to kind of figure out together why. Yes, you can call it overfit, but it's not overfit from the machine learning point of view, because I tested this on the out-of-sample data. This is out-of-sample performance, and I didn't take statistics from the future, because that's why I did separate scaling. Okay, window might be too short, but let's focus on why results look good on the metrics and on the picture, but in fact they're not good. That's what I would like to, figure out. So basically, let's step aside of the hyperparameter choice. Let's step aside of the forecasting lengths, windows lengths. Let's just focus on, okay, we have a model, it's simple and it's not optimal, but the metrics are so good, but the trading, even the simplified trading, is super not good. Sample not IID, we'll come to this. Okay, Christine, can you repeat the problem, please? Yeah, the problem is, again, that we did supposedly adequate and correct machine learning pipeline. We normalize the data, we split train and test. We check the results on out of sample. Results are good on the picture. Results actually more or less coincide with what people publish online. But if you do a simplified simulation of the trading, it doesn't work. So this is the problem. And there are at least two problems in this pipeline that are more or less that we can guess them. Position size, just imagine that position size is always constant. Again, the trading is not the key here. We can simulate it with the position size 1 or 100 all the time. What I'm checking here as a backtesting is basically just, you see, the percentage change. It's not that important. Again, by the simplified simulation, I mean that, for example, the close price was 275. I predicted that it will be 277, but so I predicted 1, that the price will go up. But in fact, it went down the next day. So the price difference is minus 0.5. And I add this minus 0.05 as a loss. Again, I don't want to focus on this. Basically, the idea is that I observe some close price on the market today. I predict it for tomorrow. But in fact, I know that tomorrow the price actually went down. That's why to my graph here of the blue performance, I put this down. And for example, if I guessed it right, I put up. So this is like the simplified picture of how we could trade in a way. This is, I don't want to focus on this because this is not the key. We just want to check out really a rough idea of the trading, but the problem is in modeling again. Yes, maybe we are optimizing the wrong metric. Again, I'll give you a hint. The data that we train is completely wrong. Both the inputs are wrong and the outputs are wrong. Even we have normalized them, they're still wrong. Yes, Luca, that's correct. Basically, the predictions here are just slugged. Basically, if you check at this picture where blue is the real price and orange is our forecast, you can see that at every step we are not predicting anything. We are just predicting what was happening yesterday. Basically, our model didn't predict anything. It just learned how to take the value from the previous day. But to the metrics that are common in machine learning, they don't know how to deal with this. That's the problem. So that's why we observe the situation. We didn't predict anything. If you took the blue line and just shifted a bit to the right, this is your prediction. We didn't learn anything. And we didn't learn, yeah, this is some sort of moving average. So we didn't learn, we wanted to predict the price in the future, but we didn't learn anything. And the problem is the key problem that our input data and the output data is not stationary at all. It is normalized from the point of view, if we had it as a picture, we want to subtract the mean value of the pixels or divide by some mean value of the pixels. It is correct if we have some tabular data, which is always in the same range and we're going to divide by standard deviation. But when we work with time series, we are interested in the stationary data, data that holds the statistics all the time. Basically, that the mean value is in general not changing and the standard deviation also is in general not changing. But if you observe even this, now let's check even normalized data when we are having this. This is our normalized output. This is not stationary time series. For example, if you Google stationary time series, why the learning had good metrics? Because metrics are chosen not correctly. I chose the metrics that are adequate in normal machine learning with the stationary and not stochastic data, but these metrics are not correct for financial machine learning. That's why, basically, that's the idea of this workshop. I want to show you how tricky everything is. And for example, this is the example of stationary time series. You see, it always has the same mean value over time and more or less bounded standard deviation. This is stationary. Again, on the left, it's not stationary. On the right is stationary. And maybe, guys, you already know how to create from the picture on the left, picture on the right. There is one mathematical operation that helps to do this. Look, the guy, I just don't know how to pronounce your name because I can't read your language. The problem with the data autocorrelation, yes, this problem is present, but I want to talk about simple things for now. Let's not dive deep at the moment. Let's look at the pictures and try to fix what is on the surface and dive deep slowly. So guys, do you know the operation how to make from the picture on the left, picture on the right? Basically, this is the common way for time series to make the stationary data. Yes, this is first difference. And at this point, I want to show a couple of slides. Basically, as we already can see, that normal machine learning is a bit different from financial machine learning. And the problem is in the data stochasticity. We can't apply these techniques, these normalization techniques, this labeling that we use in pictures, for example, and apply them to the stochastic time series. For example, on the left, there is a picture that consists of the pixels. And we know that the pixels are always bounded, and the pixel that is, for example, gray or blue, it will always be blue. Basically, this is, maybe we can normalize, because what is a blue pixel? This picture is represented with the pixels, and the pixels, for example, with the RGB scheme is a combination of red, green, and blue colors, right? So basically, we can describe every picture with the bounded set from 0 to 255 of 3 colors. And it will be always like this. And it's really easy to take this fixed representation and fit it to detect some objects. But with time series, for example, if we observe one price at one moment, it never means the same. I can tell you even more. Moreover, it never means the same like with the evolution of time. For example, on the right, this is the picture of simulated Brownian motion. The simplest example of the stochastic process that is just the random value, Brownian motion. And it looks like prices, right? But the prices can be distributed, can be generated from completely different models. And moreover, we never know this model. In the pictures, we always know this is RGB and it will be always the same. Or this is HSV and it's always the same. In text, the same. This is the word, its means more or less the same. Okay, maybe it can have another context, it can be described in some vectors, but text is always stay in the text. Text, some sentence will never change completely what it means. And with the financial prices, okay, this is geometric Brownian motion. On the next slides, that was the normal Brownian motion. Then geometric Brownian motion, jump diffusion model. Again, and this is just the models. It still looks like the prices. It still looks like the same data, the same time series, but it has completely different nature. And in the pictures or in the text, it never happens. The RGB model that you observe will never have different nature. And again, let's check another differential equations. It can be like stochastic volatility model. It can be a mean reversion model. To our eyes and how we want to treat it. That's how, because we used to do it in normal machine learning. We say, okay, this is the time series. It's bounded with some values. I'll just normalize it and that's it. But deep inside, it has completely different nature. And the worst part is that these differential equations I am showing, they never describe exactly the market. Basically, this is just the assumption that the market maybe is following one of the stochastic models with some parameters A, B, C, R, sigma, whatever, but we never know it. And that's why, for example, we can't just normalize. Everything what is related to just normalizing and treating this time series as the picture is already wrong from the start. Second point, also related to the stochasticity of the data. When you want to forecast the price of the future, again, we are dealing with such a process. Okay, I'll answer the questions. Why we... Okay, I'll just say the slides and then I'll answer the questions. Again, we observe some stochastic process with some parameters, A, B, C, D, E, etc. And we don't know how these parameters will change in the future. And that's why forecast the price, forecast this observation of the stochastic process in the future, it makes no sense. Basically, the nature of the data, the nature of stochastic processes is telling us that we can't do this. There are some complex models that may estimate the distribution in the future, on some properties of the distribution, but it never can predict the price itself. That's the problem. And when we try to forecast the price like this, yeah, basically the situation we encounter, what we see that we just predict, if we zoom inside, we just predict the observation from yesterday. This is the typical situation, because for the machine learning model, it always tries to learn something. And what is the easiest thing that you can learn from the data that is not predictable? I have a price today, I want to forecast the price tomorrow, but I prepared the data today not correctly, because it's not stationary, just some random values. And tomorrow there are some random values. The easiest for me what to do from these 2 weeks of data, and what is kind of from these 2 weeks of data is the closest data to the future. The data from today, and that's why the model in the current day predicts the data from today. That's it. This is what happens. Okay, the questions. I understand what you want to say, but I don't understand why the result of the backtest is not good. Let's say our model has a great accuracy on the test data. Isn't it okay to say backtest outcome is good? That's the point. We have great accuracy on completely wrong data. We have even great accuracy, and we even can't use this accuracy because this accuracy is not adequate. We have to choose another metrics, and that's what we're going to do today. We have to choose another metrics. And why the backtest is not good? Because all what we do today, we want to forecast the price tomorrow in order to buy or sell. And we say tomorrow the price will be the same as today. Okay, at some moments, at some points, as you can see on our pseudo backtest, at some points we actually can even go up here, because sometimes the price is really more or less the same and we guess it right. But in most of the cases the guess is wrong. That's why this is not correct. And there is also, and this finding brings us to a very important result, which is also different in finance and in normal machine learning. In finance, obviously what we want to have is a good backtest. Basically, we want to simulate the strategy, even in a simple way, and to figure out that we can have some profits from it. In finance, we have to strictly separate modeling and backtesting. We'll see in the future we can have bad performance of the machine learning models and profitable backtests. So basically, that's what I'm trying to say here. In finance, you really need to do every step super carefully. And you can mistake just in choosing the wrong metrics. You chose the wrong metrics, it shows you good performance, but you lose a lot of money on it. Basically, that's why this field is maybe one of the most difficult in the world to model. And that's why, based on these findings, I would like, because we have just 1 hour left and I want to show you more examples. Let's try to fix the problems. So we know that we need to make the data stationary in order to work not with such a stochastic process, but for example with the finite increments, the first order difference. Basically, I want to have my data like this. At least it has always the same mean and some bounded variance, so at least it's more or less kind of bounded data. It's stationary data at least. That's why I have here my second notebook. I want to do it step by step. It's loading. I take the same data. I still normalize input data as I did before. Okay, now we know it's not correct to use the scalar because we need to do these differences, to do this stationary, but I want to do step by step. Basically, I want to see incremental improvements. That's why first, what I do with the output, I forecast not the price of the future, but I forecast in how the percentage of the change of the price in the future. It's here, you see? Now my output trend tests are just the close prices. And here what I do, I take my price in the future, from it I subtract the price today and divide by the price today. What it means, for example, today price is 100. Tomorrow is supposed to be 105. What this formula gives us? 105 minus 100 is 5. 5 divided by 100 is 0.05, which is 5%. Which means now I forecast not some not stationary value. I forecast completely stationary and also normalized percentage of change. I forecast that my price will change plus 5% or minus 10%, plus 7%, minus 1%, plus 0.5%, etc., etc. And this is basically the only change I do. And my output will already be stationary. So let's see what it will change to us. Maybe even this small increment will already give us some result. Guys, I also share the code as well, so don't worry. Christina, to separate trend, stationarity, and error. Yes, this is one of the ways, but as we can see in the stochastic models, we can't really talk about the trend here. And it's a bit more tricky, because if it's some deterministic time series and we know there is some fixed trend, okay, we can do this. If there is some temporal cyclicity, for example, and we know it for sure, yes, we can use the models you said. But in finance, basically, for example, you can see here in this mean reverting process, there is some cyclicity, but in the formula there is no cyclicity. So if you will apply the normal time series decomposition here, it will find something what is wrong, because the data is not generated with the cyclicity. But you might think that there is some. Okay, as we can see now, the same model but on a completely different output, it already doesn't perform that good. And you see how important is to choose the correct metrics as well. If we check just the mean absolute error, we can say, okay, our average absolute mistake is 1.3%. Well, not that bad. But the R2 score explanation of the variability is negative. It means that actually our model learned nothing. But if we check the trading simulation, basically, okay, here is the correct result. Basically, we can see that indeed nothing happens. This is the change number 1. Let's make a change number 2. Let's use again the same framework, everything the same, but now we are prepared the input data correctly as well. This is I'll share with you the notebooks with you guys as well. Just now I want to go through them and show the things. This is basically the copy of the previous notebook. But here, as you can see, I already don't use the standard scaler at all. I selected the columns that are not stationary, which is open, high, low prices, adjustment close, volume is not stationary, this feature indicator based on the volume is not stationary, this feature is not stationary, and from them I do the basically percentage change. Basically this is you can consider it as the logarithm of the first order difference. And the output I still do the same, the percentage change. So hopefully when I fixed the 2 errors related to the data, I make both inputs and the output stationary. Maybe now it will work good. Let's see. Feature extraction, blah, blah, blah. After these results, we will discuss them again. And after discussion, a small break. And after a small break, we'll actually learn like the specific techniques for the finance that will, because what we do now, it's a spoiler, it's still not optimal. And I'll also will discuss why it is not optimal. Even this is more correct from the stochastic time series theory, but it's still not correct from the financial reality. But let's just check these final results. I'm repeating what we do now. We took the data and now we forecast not the price, but the change of the price to make it stationary, the output. And our input also we made it stationary with taking the differences of the time series. Can you repeat, please, what did you do with the features? Yes, I can. What I did. For example, this is my columns from dataset. I tried in the very first notebook, I tried to apply here standard scaler, but it didn't give me the stationary time series. So here I select the time series like high, low, open, close, volume, adjustment close, fit op volume, this feature, basically see I select them here. And I apply differentiation to them. Basically see I take these columns from the data and apply function PCT change, which is percentual change. It means that I take the first order difference, just like this, and apply a logarithm to it. So basically this is what's encoded in this operation. So this way, these features become stationary like this feature or like this feature, for example. This is what I did. And the output I left also like changes. Wow, look at this. It became even worse, which is surprising, right? Because we did things more correct. We actually made time series adequate and stationary, but the performance, look at this, it's simply nothing. But if you look at the backtest and compare it to the previous backtest, which what is even more important. Look at this. This is also an interesting point. Here, I think we even, okay, maybe it's not profitable, obviously, but here at least we're kind of oscillating around 0 with completely wrong model. And here, with a model that is slightly better, we performed so bad on our backtest. So seems like that the making time series stationary, first of all, it not necessarily helps in terms of modeling. And for example, if we didn't know that we shouldn't mix backtesting and modeling, we could say, okay, we have a bad model, but wow, the backtest is not that bad. Seems like we can work on this. This is another proof why it's so important to focus on the machine learning separately from the backtesting, because the random model can perform even good on the backtest. Just because it's random, it can be good, but it's random result. And second, basically that's what I wanted to show you again. We can build a bad model that can show good backtest. That's why this slide basically was saying backtesting is not a research tool. Feature importance is saying. So basically we know that we need to analyze machine learning models before doing any backtest. Okay, at this point, which is maybe very discouraging, I want to make a super short break, like from 3 to 5 minutes. In this break, I will drink water and answer the questions. Because I understand it's a bit too much information, but to summarize it, what we did. Very first step, we did normal normalization, normal prediction. We supposedly got good results that are visual, but it was not correct because we were using normal machine learning techniques on completely non-stationary data. Then what we try to do, we know, okay, we can apply the first order differentiation to the stochastic time series to make the data stationary and maybe to find some distributional patterns here. We did this to the inputs, we did this to the outputs, and actually it gave us nothing. From the modeling point of view, it gave us nothing both in the first and second case. And from the backtesting point of view, we even have no right to look at it right now because backtest can lie to us. So basically what we tried to do, how we tried to fix the situation, we applied time series theory and it didn't work out from the modeling point of view. And now I want to answer some questions and then I will show some financial techniques how to work with this time series to make the results a bit more adequate. Again, we will talk about inputs and the outputs, but prepare them not from the mathematical point of view, but from the financial point of view. And that will be the main difference, and you will see the difference. Basically, that's the problem of finance. It's not enough to know machine learning. It's not enough to know time series analysis. You see, for example, we know machine learning, but we got bad results. We know time series analysis, we got bad results. The problem of machine learning in finance, we need to know finance, and we really need to understand how finance works. Modeling using the right feature. Let's change the yes, Akalax channel. The problem is exactly that if the fact that you apply the better model to the incorrect data will not change anything, because the problem we have now, we still have incorrect data. And I'll show you that you can even use even much more simple models, even in the end, spoiler, linear models to get much better results than non-linear models or some boosting models, just using the right data. Because in finance, the correctly prepared data is the key, not from the machine learning point of view, not from the time series point of view, but from the financial point of view. Luca Ruzzila, what if we were to binarize the target variable? That would get us to a metric that's closer to what we want to get. Good backtesting. First, yes, binarizing, which switching from regression to classification, this is indeed a more correct metric, and it will allow us to measure the results more correctly. Also, there's another question, what exactly we classify from the binary classification, but yes, that's right. What is here not fully correct, we don't think about the backtesting before we're confident with learning part. Basically, because I show you the example where, okay, maybe that's not perfect example, but completely bad model, worse than random model, can perform not that bad on the backtest. So that's why the key is to focus on the machine learning first, and then when we are super confident in the machine learning, only then we build strategies and do backtests. Is this correct even for different outcomes such as anomaly detection? Yes, for anomaly detection is the same. Basically, what is the core of anomaly detection? You want to model what is good data and to cut everything what is anomaly, what is not good data. And in finance, again, you need to model the good data, you need to do the inputs correctly. So again, we are talking about the right preparation of the inputs. Because anomaly detection is some kind of unsupervised learning, so you have just inputs. So it depends on the case, but okay, I wait 1 minute more and I'll talk about financial techniques because we have 40 minutes left and I think this is enough to show what I wanted to show. Actually, even one day for this for this workshop wouldn't be enough. At least in one day, we could finish and make the notebook that we started to work on. We could make it almost correct. At least we could get the results that at some point trustable. That's I wanted to show as the final result of the daily workshop. But today we'll just kind of make a couple of steps towards it, and basically I want to show you the logic of these iterative improvements. Thank you very much. Thank you, Luca, for coming. I hope it's at least interesting and useful. Okay, basically, okay, this was practice time. This is what we did. We did the stationary time series, which is okay, which is basically treating our time series as it is again normal, not stochastic, but not stationary time series. This is what we did. And actually, when the very first time I saw this technique, I know it's from the book in the university, to me it was actually really weird why working with these differences is kind of better than working with the time series on the left, because time series on the left, it's super easy to me visually, because I can forecast it even without any machine learning model. I see these patterns, I can forecast it with my hands, it's super easy. But of course, when I started to learn mathematics, we realized that, okay, these differences, they describe the distribution, they are stationary, and for algorithms, this is more convenient way to work with. Okay. But since we know that machine learning is supposed to extract patterns kind of as humans do, at least in computer vision, we know that these convolutions, they learn patterns that are kind of like the same as the human brain in the visual cortex. So we also want machine learning to work with the patterns that are human-like in a way. And these differences, they are not human-like. If I watch just on the picture on the right, I can't predict nothing from it. And the problem is because this difference operation that is described on this slide, if you want to see the mathematics, this is the operator. You can take difference not only between current observation and the previous observation. You can take difference between like take previous and 2 behind this, I mean current and 2 observations behind, current 10 observations behind. And you can describe it as the mathematical operator. Sorry, this was already mentioned, but sorry, I distract myself on the question. Yes, Andrei, it should be saved on the YouTube. The streams, they are saved. The problem with this difference, the major problem, that it removes the memory of the time series. It's a really complex notion to talk about it right now, what is memory from the mathematical point of view, but intuition is like this. Picture on the left clearly has the memory and the patterns. Picture on the right doesn't really have it. And the trick is to use this operator, for example, and also there is a known fact that the more we do the difference, the more information we lose. And even if you do difference between current step and the previous step, you already lose a lot of information. And this can be described with this operator nabla with the of the first degree. This is the first order difference. If you know that the first order difference is bad and second, third is even worse, how can we do better? I still want to have stationary time series, which is kind of differentiated, but I want to save more memory. Is there a way to use the same operator, but of the fractional degree? Maybe I can use this nabla 0.5, which supposedly can give me a bit more memory. So this logic has some sense, but how do I derive the formula of the difference operator of the degree that is fractional, and how do I visualize it? That's kind of not that clear. But with some approximations, as you can see here, we can derive a formula where we can actually put the d, which d is, this is the degree of the difference in. It can be any value. It can be fractional as well. It can be 0.5, it can be 1.2, it can be 10. And the time series will still be stationary at some level station. There will be less stationary in a way, but the concept of stationarity we can define with statistical tests, so we can indeed say this is more or less stationary. But as you can see, the orange line is the time series of S&P 500, and the blue line is fractionally differentiated time series. It is still the difference, but it is the difference that saves the memory of the time series. And this is the really cool insight, a really cool technique that is not really known in public, basically. I also learned it basically from the book of, I'll show you the book later. So this is just one of the ways, this is the one of the techniques how we can make our performance better, because we got bad results here from the inputs. You see, we did the input and we completely lost the performance. We differentiated the inputs and the performance became super bad. Most probably because we lost all the memory, because we try to forecast from something that has no memory. And this is the way to fix it. Here are a bit more examples. You see the red line, I'll explain, yeah. The red line is original time series, the green line is the first order difference, which we used to use, and two blue lines show the fractional differentiation of lesser order. Marcello, can you explain why this differencing is keeping the memory? Yes, I can explain, and also I'll show you it empirically. Because if you look at this particular graph at the prices, look at the green line. Green line is 100% stationary, but green line visually is not telling you anything about if the price, what was the evolution of the price, like up or down. You just know that it started at some point, it started to get higher or less, higher, less, higher or less, but it's just oscillating around zero. You don't know what was before. And since we also have the idea that machine learning has to work with the patterns, basically I want to take 2 weeks, and within these 2 weeks I want to find the pattern that will predict the future. I want these 2 weeks also know some information kind of from the past. And this technique, as you can see, it allows you, if you take a small sub window from the blue or for the both blue lines, they can show you more evolution and more history and more memory than the green line, because green line is just ups or downs within some period of time. But blue line are ups and downs plus some memory. That's the point. This is, I know this is not deep and this is really empirical explanation, but we have just 2 hours, and that's why I try to show it on the pictures. First of all, on the pictures, and second, on the experiments. And I will give all the theoretical references, but mathematically this is correct, we got the formula, and visually it looks like this. I hope it made the explanation a bit more clear. Okay, this is the input, again, but we also have the output. And with the output we also have the same thing. And you guys in the comments, you said a really correct comment. You say that, why do I want to predict 1 day ahead? I want to predict what happened like in 2 days, in 3 days, in a week, in a month. And I completely agree with this. This is correct. But the problem is that imagine you have a model that predicts something in a week, and you predicted that from a week from now, next Saturday, the price will go up by 5%. And imagine your model is more or less correct. With this approach, there are 2 major problems. What if inside this week the price will go up by 15%? And instead of taking the 15%, you're already gonna do your deal in a week and you'll earn less, which is a problem. Second problem, what within this week the price will go down by 50% because of some error, and maybe it could be predictable, because if you have adequate framework to predict things, maybe the price will go down by 50% on the 3rd day. But you predict 7 days ahead, you put it in your code, you put it in your model, that's all what you have. But in practice, what practitioners do, they don't work like this. What practitioners do, they make some estimation for the trends, for example, with the moving average or some other approach, and they put take profit goals and stop loss limits. So they open the position, they expect the price to go up. And they expect the price to go up, for example, by 3% or something like this. And the moment it takes the 3% up, they close the deal. They earn this 3% because that's what they expected to have. That's how they can have predictable strategies. And what is stop loss? If the price at some point will go down, they say, I can afford to lose maximum 1%. And if the price within some time period goes down by 1%, they close the deal. Then don't wait till the price will go up maybe in the future. They take profit and stop loss limit. And usually this deal is open, for example, for some moment of time. If within 7 days nothing happened, I just close the deal as it is. This is how investors are thinking. This is the financial logic. So we have updated financial logic of the inputs. I want to see the patterns, I want to see the memory. And we have updated financial logic of the outputs. I don't want just to predict what will happen exactly in 1 week. I want to be flexible. And there is a way to add this flexibility to our, basically to make a data set like this. This is called triple barrier labeling. So imagine that on the picture left, what we have from the left of this red box, this is our input window. This supposedly has some patterns that will help us to predict the future. And we want to predict for some days ahead. But instead of predicting what will happen on the end of the picture, we build a barrier where the upper line of the barrier is our take profit goal and our low barrier, horizontal barrier, is our stop loss. And on the historical data, when we make the data set, we check this future window and we check what happens first. For example, if within this window, within the 7 days, the upper barrier is touched first, we label this as the price will go up. Not in a week, but within the 7 days. If the lower barrier is touched first, we say, okay, the price will go down. Not in a week, within the week. And if, for example, on the picture on the right, you can see if no barrier was touched, you can just label it what happens in a week. Yeah, that also can happen. Maybe within a week, your events that you're expecting for, they don't happen, and you just have to close the deal as it is. Yeah, that's also the option. So basically, this is the way, and also what is a good point, it leads us to the basically binary classification, up or down. It can be also extended to the ternary classification, like upper, lower, or nothing, but we can just do it as a binary, up or down, and but this up or down will be based on what happens within, first of all. So this is the two really interesting techniques. Again, they normally don't appear in the literature a part of finance, but they are a better way to work on this. Yeah, and again, based on this, we can do the modeling, but I really want to repeat it, and it's really super important, that backtesting, you do it as the very, very last step. Before doing the backtesting, you want to ensure that your model, your data is completely correct and you validated it correctly. By the way, what we are doing here, taking past and predicting the future, is also not correct. Because in machine learning, there is a cross-validation actually, and here what we do, we don't do any cross-validation. We just took one random sample, it tried to overfit on this one random sample. It is also not correct. So we need to focus on the modeling first. And modeling involves getting the right data, preparing the right inputs and the outputs, training the model correctly so it doesn't overfit, validating the model correctly, validating with the right metrics, and only after, when we're confident, when, for example, on the cross-validation in some way we saw that, okay, our distribution of the accuracies or F1 scores or something like this is good for us. For example, on average, on this k-fold validation, we have 55% of accuracy, and we're confident in this. We freeze the model and we do backtesting. And the most important part, if we have a model that is supposedly is good, for example, 60% of accuracy, but on the backtest it doesn't work, we go to the start, do some changes, and we don't do the changes in order to make the backtest better, because this way we can justify some random patterns. We know that in the modeling part, 60% is not enough. This is the market. The market is driven by a lot of good predictors, so if you make the market with 60% of accuracy, it's not enough. That's the fact. It means that we need at least, for example, 65% of accuracy. We don't check the backtest anymore. We do the modeling until we get the 65% of accuracy. And if we don't get the 65% of accuracy, we don't try to play with the backtest. We say, within the current data set or our current capabilities, we can't work on this market. That's it. Because justifying the model and tweaking it to make the backtest look good, that's not correct. Because diving deeper into details, what is the backtest? Backtest is how your strategy could perform in the past. And you expect it to perform the same in the future, which sounds adequate, but the backtest, this time series of Apple in the past, what it is? It is stochastic processes from some family of stochastic processes. Apple could go in the past and can go in the future in many different ways based on some stochastic model. And basically doing the backtest just on one simple time series, that's already not correct. That's why practitioners, for example, they do the simulations. At least they do the simulations. They try to fit the stochastic differential equation to the data, sample different potential outcomes, and they see how their strategy would perform on these outcomes. Only this way we can more or less trust something. Okay, let's apply these both techniques to our data and to see what it changes or what it doesn't change. Again, the code I'll share with you. For example, the routine for making this triple barrier. Okay, this is coded by me. It's maybe not the most optimal code, but at least I understand I can control it. I'll also share with you the library where maybe there is a better code that you want to use, but I feel myself more comfortable with the self-written function where I control it. So this is the function that gets this barrier. You see it takes future window, it takes minimal, basically, some hyperparameters like take profit, stop loss. If I want to use this vertical barrier, and it returns me unit variables. And fractional differentiation, I want to show you a bit more things. I promised to show you why first order difference loses the memory, because okay, I give you the picture, but I didn't show you empirical results. Yes, that's what I forgot to show. Checking differentiation, that's what I wanted to show with you guys. Let's again take the close price. It's called test. This is the stationary time series. And there is the augmented decay Fuller test that is testing the time series for the stationarity. I can run this test. Basically, the idea is the smaller the value I have of this idea of statistics, the more stationary the time series is. Of course, there are also p-values, etc., but for us, it's enough to look just on the first number here. For example, this time series itself is first order difference. And this is basically, it's low enough value. And look, if we take a difference from a difference, which is as we know, second order difference, the time series become even more stationary. Wow, which is good, but we know that we lose some memory in this. For example, if you take cumulative sum of this time series, it will make it, a hint, not stationary. You see that the value is getting much higher. So intuition we get. The smaller value we have here, the more stationary time series it is. This is our input time series, work time series. This is our Apple price, and this is the first order difference on this image. And just calculating again the. Okay, you see the original time series has value 2.5, first order difference value minus 10. This is our measure of stationarity, and we indeed want time series to be as most stationary as we can. The small test I want to show you, and this is really the simplest measure of saving the memory and saving the information, is the correlation between two random variables. If I think that my input original time series that is not stationary but it contains all the patterns is 100% of memory, and I want to measure the loss of the memory, I want to see the correlation between the new time series and the original time series. And if the correlation is high enough, maybe I save the memory, because these two signals, original and differentiated, are more or less like, at least they correlate with each other. And if I check the correlation, you see that it's really very low. The difference, the first order difference and the original time series has correlation of 0.7, which is 0.07, which is nothing. And second order difference has almost no correlation. So this is the empirical proof that even within such a simple measure as correlation, we lose almost all the information. So in practice, what I want to do, I want, of course, I want to balance between the stationarity and this correlation as a measure of the information. And from the statistical tests, I also know the p-value, basically the value that is telling me that, for example, here, what is this? This is telling me that with the 95% of, how it's called, confidence, if my ADF value is this, then it's stationary, or this, or lower than this is stationary. So I want to build such a fractional differentiated time series that has the ADF statistic value less than this, but still it has as high correlation as possible with the original time series. This way, in the loop, I'm sorry guys, it might be a bit in the rush, but you'll be able to check all the notebooks later. So that's why in the loop, I'm checking different options for this diff value, for this D. It can be 1, 0.5, 0.6, and I plot, it's working, not working. And I'll plot these values. Okay, this is my, for example, difference order of 1. It is super stationary, but the correlation is around 0. And I expect to see that, for example, with D around, you see, for example, D 0.1, the ADF statistics is way too high. Yeah, the correlation is good, but my cutoff value of the ADF statistic is minus 286, as we discussed. So my optimal value, I think, will be 0.7, because with D 0.7, my ADF statistics is minus 3.40, minus 3.4. Correlation is 60%, which is not bad. And with 95% of confidence, I can say that my time series is stationary. So that's why here I'll put the value 0.7. And my time series will be like this. Then from this time series, I'll extract a couple of new features. Basically just statistical features. I want to take the mean value, standard variation, skewness, kurtosis, autocorrelation, and I want to use this as a feature set, because since it is already contains some memory, I might think that this value is stationary and it contains the memory. I will not use the window anymore. I'll just use my features from the single day, because it already has the memory and I assure that I have the memory. Okay, this is original time series. And for example, you can see my new feature, where they are. For example, yeah, this is my mean value, standard deviation, skewness, kurtosis, autocorrelation, based on the fractionally differentiated time series. Here I create the data set based on the triple barrier logic. No time to dive into it. Just I'm applying this method to build the labels. And the inputs are these features, as you can see. But not windows, but now from a single day. From I take not a window, but a single day, because I know that in differentiated time series, I save a memory even a single day. And here I want to build a couple of experiments. Also to show you some interesting properties. We all know that the gradient boosting classifier, this is something what is powerful algorithm. It's maybe it's even better on this kind of data than neural networks. And the problem is that like random forest and boosting algorithms, they're based on the bootstrapping, so they kind of sample the data. That's why, as you can see, I will run the training 50 times, so I can have like a distribution of different accuracies. I calculate the Matthews correlation coefficient to have a single measure of the accuracy. Basically, it's the correlation between prediction and the true value. And we'll calculate it and we'll see how will be the accuracy. It will take some time, but the results maybe will be surprising for you. Again, I'm running the algorithm 50 times because inside of the algorithm, the nature is stochastic. It samples the data. That's why if I run algorithm again and again and again, I get different results. That's why of course, I could fix the random seed and everything, but I'm curious to see the distribution of the results. And oops, the correlation is negative. So even if we did everything correct, correlation is negative. It means that we have no right to go to the backtest. We need to make correlation at least the positive, so we can trust our machine learning model at least somehow. Now I want to show you a trick from the book, which is I'm not going to explain now, but you're going to read it in the book, or in the slides of the professor I'll send you as well. Instead of boosting of the trees, I will use bagging of linear models. What boosting does? Boosting builds a lot of simple tree algorithms that one above one improve the accuracy of the previous one. Bagging classifier is sampling from the initial data set different samples. On all the samples, train separate model. In our case, it's even much more simple, linear model, and then averages the predictions of all the models. This way, it's supposed to reduce the variance, because if you sample from a data set many parts, so this way each of the linear models trains like maybe different patterns. And wow, what a surprise! Bagging of linear models works better than boosting of the trees, which are better. Based on this, now we have right to run our simple backtest. And the backtest, as you can see, if the probability of the price to go up is less than 0.5, we go short, and otherwise we go up. And as you can see, even with the good model, you have the bad result of the backtest. It also can happen because we have the bad logic of the trading. I'm sorry for being a bit of the rush. We have just 10 minutes left and I want to be on time. Instead of having such a binary prediction like, okay, I go -1 short or 1 up, I will use the probability of going up or down. So basically, if my normal stake is $100 and based on my prediction I put 100 up, 100 down, if the probability of the price going up is 60%, I better put $60 up. Or if the probability to go down is minus 20%, I put $20 down. And if I change the logic to this, as you can see, at least this is trustable machine learning model at some point. And all my strategy trajectories are more or less around each other. So at least I can estimate my risk here. It doesn't outperform the time series of the Apple. So basically it's still much more profitable to invest in Apple, but at least this is trustable at some point. Or not really, guys, because actually in this task we made a lot of mistakes. Sorry, again, it's a rush, but I want to finish up the materials. First of all, if we would do the exploratory data analysis of the variables and we could use some correlations, we have no right to use the correlations because correlations, they show the linear dependence, and finance, there are no linear dependence. Second problem, when we were sampling the windows for training, they were overlapping. And when the windows are overlapping and the corresponding outputs are overlapping, we are violating the hypothesis that our data is independently distributed, because it's dependently distributed. Windows are dependent on each other. We didn't do cross-validation, as I said. I did a small trick, and actually in all the time in this data set, there were 5 variables that are completely random. I just called them to make you kind of believe that they're correct and everything, but the variables that is dividend, sentiment, K10 feelings, fundamental 1, fundamental 2, they are just random variables distributed with different random distributions. And actually, that's why the model we did, we still can't trust it, because we didn't do feature importance. And if we did feature importance, we could see that these 5 features, they don't contribute to the model at all, and we should analyze it. Again, we didn't do the correct backtesting. Again, probabilistic interpretation, we kind of did it, but still there's a long way to go. And okay, we didn't do anything with the hyperparameters. So even in the end, we came out with something which is more or less trustable, because here distribution is positive, here also the variance is not that high, but it's still not correct, guys. And this is just some of the mistakes that we did here, and these are important mistakes. As a homework, I'll share with you the materials, the code and presentation, the video will be on YouTube, and I encourage you before the next meeting, online or offline, or maybe there will be no meeting, let's see, to work with the data, try to fix the variables, extract something new, play with the data. The modeling part. The thing that I didn't explain at all is why bagging of logistic regressions works better than boosting of the decision trees. This is for what I suggested to check the book of Dr. Lopez de Prado. Also, I suggested to check the feature importance, and you can check it in my blog, for example. And as the motivation to do research in the field, check the papers, top 5 papers on machine learning and stock price prediction, and find the mistakes. All the mistakes we did today, basically most of the works are the very first notebook that we did. The goal of this homework is not to get the best accuracy possible, because it's super difficult task. I want you to focus on the maximization of the trust to the model. And backtesting is not a research tool. Also, there are interesting research direction, but you'll check the slides later. There are where deep learning can be applied, etc., etc., etc. To study materials. If you guys are really new in the field, I suggest you to check Quantopian lectures and these 2 books on the QuantStart website. These 2 books are showing not completely correct approach. Basically, these 2 books do some mistakes, but they show you the pipeline, and I think they're good to start to get some literacy. Then I really think important that in financial mathematics, I think it's important to understand the data nature. And I think without knowing some stochastic calculus, how some options, future and other derivatives are created, it's very difficult to go, because you really get the feeling that the prices are stochastic only after you study stochastics. Before, to you it looks like, okay, it's a picture, I'll just apply convolutional neural network, but it's not like this. And these 3 books are one by one giving good practical, theoretical and practical explanations. And the last, basically most of the walkthrough from this workshop today is from this Marcos Lucas de Prado book, Advances in Financial Machine Learning, and also some really wise thoughts and practices related to the topic are in this Coursera course. This is what I suggested to check out. And as the last step to really, maybe someone got super motivated, there is financial forecasting tournament on this website. Also suggested to check it out. Okay, so this is basically all what I wanted to show today. We are at time. And I think that the real goal was this. I hope that everyone who is a practitioner from now will adopt your pipeline, because what happens in finance can happen in other fields. And I hope that even if you're never going to work with financial data, now you think a bit more carefully about preparing your inputs, preparing your outputs, about normalization, about the models, about because backtesting basically is kind of like qualifying the business value. And also maybe you can think in your business applications, you also can think about how to measure the business value correctly. So basically this is what this workshop was about. I will add code materials both behind the YouTube link in the description and in the meetup group. And I hope that we will make the second part of the workshop where basically we will finish this exercise and we will fix all the sensitive points, and we can say, okay, we did something what is as most correct as possible we can do. Thanks everyone for coming. Appreciate it. I hope it was interesting. And yeah, have a nice Saturday, Sunday. Take care of coronavirus.